Okay, so in this chapter we're going to derive our kinematic equations. But before we do that, it'll make sense for us to first dig into a little bit of notation first. And I'll try to keep this video short enough that it's easy to come back to as a reference throughout the next coming weeks. I will also put these equations underneath the video on the chapter. Let's start with a reference frame. When I'm calling out a reference frame, I will use the notation with curly braces around an uppercase letter. So some examples would be the global reference frame. I could have another arbitrary one named A, and we'll commonly have one called R, which is the frame of reference attached to the robot itself. And a frame is usually accompanied by some sort of diagram. And I'll denote on each coordinate, so the x and y coordinates here, the frame for which those represent as a superscript on the left-hand side of the coordinate symbol. In addition just to having a frame, it's useful to discuss a relative frame. And the notation we'll have for indicating that one frame is relative to another. So let's say that we have two frames, A and B. And let's say that A is a static, it's a fixed frame, and B is one that moves around. And what we want is to define B in terms of A. For that, we need two things. Some way to represent a change in orientation from A to B. So that's what R stands for, it's a rotation matrix. And then an offset, a point. So if I'm talking about one frame relative to another, you should have these two entities in mind. So for example, I could have my frame A and a different frame B. The point is the origin of frame B represented in frame A. So there's really nothing fancy about a point P being defined in A. It's really just a point in that original frame, the static frame. The rotation matrix, on the other hand, takes care of the second part. So imagine I take the same picture and we treat these two things as separate operations. So let's ignore the offset and just look at the rotation. You can picture that rotation as if you were superimposing the B frame on top of the A frame and then trying to just compute this angle here. So a lot of times you'll see me write a relative frames rotation matrix, so this quantity here, from A to B given some theta, given some angle of rotation from one to the other. And we'll dig into this a little bit more in subsequent slides, but this is a 2 by 2 rotation matrix, because everything that we'll be doing this semester just lies in a flat plane. And depending on the value of theta, we can fill it in like so. A few additional pieces of notation to keep in mind are how do we define a point in a frame? I actually just previewed this in the previous slide, since I mentioned this is a point in a frame. But it's essentially just some capital letter with the frame in the superscript on the left-hand side. And a point is really going to represent two values. It's going to be, for us, a column vector with that point's x-coordinate and that point's y-coordinate. And it's important to consider it a column vector, but I'll still usually write them horizontally just to save space on the screen. And here's just a note saying that the point is usually going to be an uppercase letter. This value here is the transpose, which just means it's going to take something shaped like this and turn it into something shaped like this. It's my way of writing this as a column vector but putting it horizontally. Next, we could have a vector in a frame, and I will do my best to keep those as lowercase and slightly cursive looking letters. And similarly, it's going to have components, and it's going to be a column vector. I also gave a preview of this next item. But let me more formally define it. This is a rotation matrix from one frame to another. So this is B being expressed in A. Another way to say that is it rotates from B to A. And I'll resist the urge to recopy the values from the previous slide. The values shown here in the table. So that's a rotation from one frame to another, but a full transformation or change in reference will require both the rotation and the offset component. So a change in rotation will look something like this. So let's say we have some point, and I'm going to call it Q since I used my variable P above. So we'll have some point. And that point can be defined in some frame. So let's say this one happens to be defined, the values, if you were to look at them, the two values for that point are defined only with respect to the B frame. Let's say it's important for us to know what those values are with respect to a different frame. It doesn't have to be a fixed frame, but just some other frame. Well, we can rotate the point, which we do by pre-multiplying by the rotation matrix. And then we need to make sure we include the offset. So that would be some point P, taking us from the origin of one frame to another. This notation and the way that I'm using superscripts and subscripts is really just all set up for this particular equation here. The way you're supposed to read this matrix multiplication is that we're canceling out the b's, so that we're left with some matrix R times the matrix Q, the b's cancel out, and we're left with a matrix with just an A remaining. So an A here and an A here being added together. So I'll make that note. You'll often see this put slightly more compactly, like so. Where this T transformation matrix, instead of just a rotation matrix, takes into account both of those operations at the same time, this rotation and the offset. Instead of being boring and just immediately giving you what this transformation matrix looks like, we'll sort of discover why this is useful as we go through the next few slides. But I'll make sure to update the chapter website with all this information right underneath this video. In the next video, we're going to start putting these together and start figuring out how this notation is useful for describing the robot's motion.